So you remember all this where we had to list every possibility and it was just way too much unless it was super small like that, but that one you could just kind of go around anyway. But then we got to one where we're like, man, that's just too big, and we didn't even list everything because it would have been so many possibilities, and then it just gets really big. There's got to be a better way. Now, I'll go ahead and tell you, this better way that we're about to learn is one of three ways. This is the first way, first method for solving the traveling salesman problem. And again, traveling salesman problem meaning you start in one city and you go to all the other cities and you find the cheapest route and you go back to where you started. So that's the main idea behind it. That's why it's called that. But it's one of three ways, and this is the second of the ways. However, the first way we learned always gives you the cheapest, but it might take several millennia to list all the ways, right? So yeah, let's not do that. So why don't we just choose the cheapest route as we go? Let's do one. Let's start and end in Atlanta. This is actually the exact same problem we started with yesterday. And we might get the same answer, and we might not. So we just need to follow this process, and let's go. So we're going to start and end in Atlanta. So if we begin in Atlanta, I'm going to just find the cheapest flight out of Atlanta to one of the cities I want to go to, and that would be for 149 to Denver. So we're going to go ahead and go to Denver. Now, at this point, we have some options about what we could do. We could go to Chicago, or we could go to Buffalo, and I would like to call it the nearest neighbor, and that is, of course, what we're calling it, but let's not consider that this one actually is the cheapest. So once I get to Denver, I'm not going to say, oh, let's find the cheapest. Well, that takes me back to Atlanta. So I do have to limit my options as I go, just kind of keeping common sense in mind and the fact that we shouldn't complete our circuit too early, right? So from here, from Denver, we are going to find the cheapest one to a city we haven't gone to yet. So we're going to Chicago and Buffalo. Cheapest one of those is Buffalo. And at this point, we would love to find the smallest number. And it actually is the city that we're going to be going to, but it may not always be. So for example, if the 199 would have been smaller, I still wouldn't take it because it would put me back in Atlanta, and I haven't been to Chicago yet. So again, the whole purpose is to visit every city. So you're going to get to a point where you say, you know what, I just haven't been to Chicago yet, and I have to go. So there we go. And then we go back. So that seemed awfully quick, didn't it? Yeah, it did. Let's write it down. So we're going to write down our circuit, and it begins in Atlanta, and it goes to Denver, and then it goes to Buffalo, and then it goes to Chicago, and then it goes back to Atlanta. And when we do that, we actually still have the $743 circuit that we had completed earlier. All right, we have a few steps that we can use when we follow this process, and I'll write them down for you. So here we go. To use the nearest neighbor algorithm, we will start at our starting point. So from your starting point, find the cheapest route. And I'm going to call it the cheapest route, but I do want to put it in the context of this lesson, which is called nearest neighbor. So we're going to really call it the nearest neighbor. Now, nearest might sound like distance, but in this case, we're really just looking for the lowest number, whether it's miles or whether it's dollars or whatever it represents. We're looking for the shortest, the cheapest, the smallest, whatever it is. So from there, from the second city, second vertex, we'll call it a vertex because it may not be a city. It might be not a city. It might be you're mapping out the quickest way to send circuits on a circuit board, so from one spot to another. So from the second vertex, find the nearest neighbor that you have not visited yet. Now it sounds like we're going around in the neighborhood and visiting people. And then also in step 2, I'm going to put repeat. So then from the third vertex, and then from the fourth vertex, and then from the fifth vertex. And then when you're done, add. That's it. So you find the cheap one, then you find the next cheap one, to a vertex you haven't been to yet, and then you find the next cheap one to a vertex you haven't been to yet, and then you find the next one to a vertex you haven't been to yet, and then you just add. Okay. Use the nearest neighbor algorithm to find the possible cheapest. It may not be the cheapest. This is a fast way, but it is not always the cheapest way. Sometimes it is. Cheapest Hamiltonian circuit that begins and ends at A. So let's start at A. From A, we will find the cheapest route or the nearest neighbor. So from A, let's see, 18, 15, and 17. So we'll take the 15. Now, also keep in mind that the shortest one may not be, the shortest one on your picture may not be the smallest distance. Based on the way the scaling is, it might not. See, for example, the 17 and the 18 look about the same, but obviously this one's 17 and that one's 18. So they're not necessarily going to be based on the distance you see on the paper. Just throwing that out there. Okay, from here, we're going to pick the cheapest one we haven't been to yet. We've already been to A. We have to go back to A when we're finished, but we can go to either B or D, and that one is the one we're going to go to next. And then we're going to pick the cheapest one that we haven't been to yet. Well, the only one we haven't been to is D. So you might say, man, 18 is smaller. I hear you, but then you're just making the triangle, and I don't want a triangle. I want to visit all four sides, not three of them. So, all four vertices, sorry. Proper vocabulary here. So there we go. A, C, B, D, and then we go back to A. So we're going to write the numbers in there. Let's do that. So A to C was 15. C to B was 11, then 22, and then 17. And then we will add those together. So 15, 11, 22, and 17. We'll add those together. It's a little bit too early in the morning for me to be doing this in my head. Actually, no, I will do this in my head. 26 plus 22, that would be 48. 48 plus 17 is 75. No, it's not. It is 65. And it is $65. There we go. All right, let's flip this paper over and keep going. Oh my goodness, they get bigger. Well, don't panic, because we're not listing all the possibilities. And these go pretty quickly, actually. So let's do it. Let's do this. Let's start at A, because they said so. And we're going to find the cheapest one from A. Now, the tricky part about this is what number goes with what line. I'm trying to configure it to where it's obvious, but still sometimes it gets a little tricky. So from A, we're going to find the cheapest. So 88, 41, 62, 93. Now, let's talk about what we see on the paper. The shortest one looks like 93, but it's actually the biggest number. So again, don't be like, ooh, that one's closer, and ignore the numbers. No one ever does that hardly, but just in case you were thinking that, let's not. So 88, 41, 62, 43, 41. Okay? Now, I still need to go to D, B, and E, and I'm going to pick the smallest one I see. 98, 114, and 59. That would be 59. Okay, I still need to go to D and B. So I need to look at the 60 and the 48. Let's go to 48. And now you could say, oh, look, 107 and 88. The shortest one's is 88. So no. That would take you back to A. I still haven't been to B yet, so I have to go there at this point. So there's really not an option. Once you get down to like one vertex you haven't been to yet, you have to go. There we go. And then we go back to A. So let's list those in the order we had them. Now, by the way, you could list this backwards, and that's okay. A, C, E, D, B, and then back to A, and we'll put our numbers in there. 41, 59, 48, 107, and 93. And when we add those together, we're going to get 348. And that is the cheapest one we found with this method. Maybe it is the cheapest one, and maybe it's not. We really don't know, but that is a very efficient way of finding a cheap way of doing things. All right, have a couple more. Let's go through them. Things get a little bit tricky here. So we've seen this configuration before, and we're going to start and end at A. So from A, we will pick the shortest, so 13. Or the nearest, the cheapest, call it whatever you want. It's the least. So from here, we will pick the cheapest one we haven't been to yet, and we have to be careful. So let me flip back over and go back to the directions. From the second vertex, find the nearest neighbor that you have not visited yet, and then repeat. And that the way I worded it here kind of falls apart, so we really need to be cautious because the cheapest one I haven't visited yet is B. And you know, that's great. We can go to B, but again, we did this in the last set of notes. When I go here, I've blocked myself off. So if I truly pick the cheapest, then I'm thinking, okay, well, I gotta go get these and then come back through, and then that's not very efficient to go back through. Let's not. So even though 14 is the cheapest, that's not gonna work, because if I drew this, boink, then I can't go down and get these without passing back through where I've already been. So we have no choice now but to just dabble with these down here. So B really isn't an option yet. So 15 or 22 would be 15. And again, don't go back to B. So I would love to say, oh, well, we haven't been to B yet. Let's go to B. And that's great. But no, what about D? So 23, 11, 17. So sometimes you don't pick the cheap one because you have to cover all the ground that needs to be covered, and you're going to block yourself off otherwise. So A, C, E, D, B, and then back to A. And let's put some numbers in there. It was 13, 15, 23, 11, and whoops, 11, and that one is 17. We'll turn that into a 17. And when we add those together, we're going to get $79. Miles, who knows what it represented, but there you go. All right, we have one more, and this one's going to get very, very tricky. So here goes. We are going to start at A. My. Let's start at A. Let's go to the cheapest one, 4, 10, or 5. 4. Now let's go to the cheapest one, 15 or 11. 11. Now, as I get deeper into this part that looks really confusing, I need to be careful that I don't block myself off. Meaning, like I would do up here if I would have gone A, C, B. I'll never get these down here. You know, I need to be cautious. So I'm looking 3 and 13. 3 is obvious, and actually, yes, let's do 3. Now I look at this and I see the 2, but let's not do the 2. Because if I go 2, then how am I going to go back up and get that D? If I do this, I got to go up and get this, and then I'm passing back through one I've already been through, which is not very efficient. So let's not get the 2. We have to make sure we complete the circuit. So we're going to have to go up and get that D, even though it's not the cheapest. And then we have to come back down. Okay, at this point, you really don't have too many options. So you've got to go back to A, and there's really only one path that will complete the circuit. So let's go 8 to G, and then 7 to H, and then 5 to A. And that is going to be what is possibly the cheapest way of doing this one. Now, if we were to list all the ways, good luck with that. So we had A to B to C to E to D to F to G to H to A. There we go. Let's put some numbers in here. 4, 11, 3, 6, 5, 8, 7, 5. When we add all those together, 49. There we go.